In episode 47, titled Map OSI and TCP/IP Models to Security Controls, we translate layered networking models into everyday placement of safeguards and the reasoning behind those choices. The aim is not to memorize 7 boxes or 4, but to make layers a thinking tool, a way to predict where a threat will manifest, where evidence will appear, and where a control will be most effective with the least collateral cost. As we move through each layer, we will tie defenses to concrete artifacts, configurations, logs, packet captures, and approvals, so the model becomes a practical map rather than a diagram on the wall. By the end, you should feel comfortable tracing a request up and down the stack and explaining why each protection belongs exactly where it sits. A brief anchor helps before we place controls. The Open Systems Interconnection (OSI) model describes 7 conceptual layers from the physical wire to the application that a human or program interacts with, while the Transmission Control Protocol, Internet Protocol (TCP/IP) model condenses those concerns into 4 transportable buckets. The value of these abstractions is design discipline. They help us isolate causes, align countermeasures with where risks enter, and avoid mixing responsibilities that produce brittle systems. When a failure shows up as garbled frames, we look to the lower layers. When it appears as broken sessions or corrupted payloads, we focus higher. Layers guide both prevention, by placing controls at the first effective choke point, and verification, by telling us which signals should prove a control is working. At the physical layer, the controls are wonderfully unglamorous and absolutely decisive. Cabling pathways are locked and labeled. Patch panels and intermediate distribution frames are in access-controlled spaces. Unused switch ports are administratively shut and, in sensitive areas, covered with physical port locks. Environmental sensors track door openings and tamper states, while camera coverage shows who touched what and when. Inspection does not guess. It walks the closets, tests that dark ports truly refuse link, confirms that spare small form factor pluggables are inventoried, and checks work orders against changes observed on the floor. The evidence that something is protected at this layer is tangible: keys, badges, seals, and denial of link, not just a policy line. Moving to the data link, we shift to how neighbors share a medium and how switches forward frames. Media Access Control (MAC) filtering blocks unknown devices in contained networks, while Virtual Local Area Networks (VLANs) separate broadcast domains to reduce bleed between tenants or roles. Switch hardening removes dangerous defaults. Management on out-of-band networks, disabled unused services, storm control to dampen floods, and dynamic host configuration protocol snooping to kill rogue address assignment. The proof lives in switch running configs, port security violation counts, and sampled frame captures showing correct tagging at trunk boundaries. A small but meaningful test is to plug in an unauthorized device and watch the port drop while the log records the attempt with a date, a port, and a MAC address. The network layer is where addresses route and where many threats can be filtered efficiently. Access Control Lists, ACLs, deny unnecessary paths by source, destination, and protocol. Anti-spoofing rules validate that ingress traffic bears legitimate source ranges, and route filters keep undesired announcements out of the control plane. Internet Protocol Security, IPSec, protects flows that must cross untrusted links with policies that pin cipher suites and lifetimes. Validation is empirical. Traceroutes prove paths, packet captures show time-to-live behaviors and header flags, and router logs demonstrate that bogon sources are dropped at the edge. When this layer is healthy, only expected networks can talk, and they can do so with integrity preserved across the hops that matter. The transport layer is where reliable streams and datagrams are managed, and where we typically anchor confidentiality and authenticity in motion. Transport Layer Security, TLS, versions, ciphers, and certificate validation rules are enforced at these boundaries, ensuring that the handshake is both modern and properly verified. Preferred suites use authenticated encryption. Session resumption avoids unnecessary exposure, and certificate chains are pinned to trusted issuers with clear rotation ceremonies. Analysts confirm health by reviewing handshake transcripts, verifying server names and certificate dates, and monitoring failure codes that indicate drift or tampering. The security story here is not a padlock icon. It is a documented proof that peers are who they claim to be and that data is unreadable to eavesdroppers. The session and presentation concerns sit between transport and application, and they frame how conversations are established and payloads are made safe to interpret. Token handling defines session lifetimes, refresh patterns, and revocation semantics so that identity is stable yet short-lived. Serialization rules constrain formats such as JavaScript Object Notation, JSON, Abstract Syntax Notation, ASN1, or protocol buffers to eliminate ambiguous decoding. Input normalization ensures that equivalent strings are treated the same before validation, which prevents double encoding and case tricks from slipping past filters. Reviewers look for diagrams of token flows, parser configuration that disables dangerous features, and test cases that prove an input yields exactly one normalized representation. When this layer is sound, applications do not carry the burden of guessing what a request really meant. At the application layer, we meet the logic that users and services perceive, and protections become precise to business intent. A web application firewall, WAF, enforces syntactic and semantic rules for endpoints, while authentication binds users or clients to accounts, and rate limiting keeps resource use inside safe bounds. Logging captures request paths, identifiers, and decisions in a form that can be reconstructed for incident review without exposing secret values. Strong controls here are explicit, well-defined allow lists for methods and parameters, clear error handling that yields stable codes, and protections that degrade gracefully under load. The artifacts include configuration snapshots, sampled sanitized logs, and playback of tests that show the WAF and application logic agree about what is permitted. Attacks love ambiguity, and mapping them to layers shrinks that ambiguity. Address resolution protocol poisoning is a data link problem with switch defenses and sensor evidence in gratuitous replies. Border gateway protocol route leaks are a network layer failure solved with strict filtering and observed in control plane logs. TLS downgrade attempts press the transport boundary and are blocked by version and cipher negotiation rules. Serialization bombs live in presentation parsing and are diffused by input limits. Injection flaws manifest at the application layer and are mitigated by parameterization and canonicalization. The virtue of the model is clarity. Each threat has a first-class home where it can be detected early and countered cheaply, even if additional guardrails exist above. Monitoring spans every layer, and analysts rely on signals that correspond to where problems originate. Physical anomalies show up as unexpected link flaps, power alerts, or door open events tied to device outages. Data link health is visible in interface error counters, port security violations, and VLAN tagging inconsistencies. Network layer detection uses flow records, route change logs, and denied ACL counters to trace lateral movement or beaconing. At transport, handshake failures and certificate validation errors tell a story about impersonation or misconfiguration. Session and presentation issues surface as token verification failures and parser exceptions, while application signals include spikes in error codes, WAF rule hits, and unusual latency distributions. Good detection design teaches teams to read these signatures like a language. Dependencies run downhill. A strong application policy cannot save a path if the transport will not negotiate secure ciphers, and perfect transport does not matter if network routes leak traffic to untrusted peers. Data link misconfiguration that allows unauthorized devices can render network policy meaningless, while physical access that permits rogue taps can make all higher layer assurances performative. This is the sober reason to treat layers as a chain. The strength at the top is bounded by integrity at the bottom. Sound engineering therefore pairs top-layer feature work with periodic reviews of the layers underneath, capturing not only that a control exists, but that its supporting strata are still enforcing the assumptions it relies on. To see the full path, follow a single API request for a payroll approval across the stack. In the wiring closet, the port is locked, the switch recognizes the expected MAC, and the VLAN tagging places the host in an admin segment. Network ACLs allow only the payroll subnet to reach the gateway, which negotiates TLS 1.3 to the service endpoint with a certificate verified against a trusted issuer. The session token is validated and normalized. The presentation layer accepts only allowed content types. The application enforces role-based checks and rate limits update calls. Evidence accumulates at each step: a port security log, a flow record, a captured handshake transcript, a token verification entry, and an application audit record, tying user, action, and outcome. One request, many layers, each with a control and a receipt. A quick diagnostic test can build useful intuition. When an alert mentions excessive retransmissions and failed handshakes after a certificate change, the most precise starting point is the transport layer, confirming version and certificate validation before escalating up or down. If users report that only devices on a newly installed switch lose connectivity while others in the same floor work fine, aim first at the data link, checking VLAN assignments and port profiles. If a service suddenly starts sending secrets in clear text after a library update, the presentation and application layers deserve immediate scrutiny for serializer or header regressions. Practicing this triage language out loud is not busy work. It is how teams move quickly without creating new problems. To close, convert this layered reasoning into a living control-to-layer map for one production service. Start by naming the service boundary. Then write one short line per layer that states the control intent, the mechanism in use, and the evidence you expect to review monthly. Include the dependencies that support each choice: cabling and closets for link assurance, switch profiles for VLAN separation, ACL changes with approvals for routing, certificate chains and cipher policies for transport, token and parsing rules for session and presentation, and WAF and authentication policies for the application. Keep the map pragmatic and current so that when the next change or incident lands on the desk, your team can point to a specific layer, a specific safeguard, and a specific artifact that proves it is working as designed. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.